Okay, I'm finally back. Today we're going to go over the alternating series test, which is a way to test convergence for series that have terms that alternate in signs. Now, there's something special about this test that I'll go over in a little bit, but in the meantime, let's go over the conditions for a series converging by the alternating series test. Now, there are three conditions. The first one being that the series terms must alternate in signs. For instance, each term must go from positive to negative to positive to negative, or vice versa. Each term also must be smaller than the last. And the limit as n approaches infinity of a sub n must equal 0. Now, if you want to identify an alternating series, look for these two terms. The first one being -1 to the power of n. And I'll show you why in a moment. In fact, I might as well just do it right now. So if I were to give you a series consisting solely of -1 to the power of n, the terms would look like this. 1 minus 1 plus 1 minus 1. Now, of course, there has to be more to the series than this. However, you can see that this does cause the series to alternate in signs. Likewise, cosine n pi or sine n pi does the same thing, as I'll show you in a moment, because if we were to substitute the first term in, if we were to substitute 0 in for n as the first term, we'd see that we end up with cosine of 0, which is 1. But if we were to substitute a 1 in for n, then of course we end up with the cosine of pi, which is -1, and this continues onward indefinitely. So those are the two terms. Well, I suppose there are more. Those are the two most common ways to identify an alternating series. As I stated earlier, there is something else you have to test for with the alternating series test, and that is if the series converges absolutely or conditionally. Now, the series converges conditionally if and only if the original series converges. Now, it converges absolutely if the original series converges and the absolute value of the series converges. This is the only series test in which you have to prove this. So this is practice problem 1. Let's first try to rewrite the series to make it to see if it actually alternates. So you can see that we can rewrite -5 to the power of n as -1 to the power of n times 5 to the power of n. And that's because -5 is simply just -1 times 5, and we're separating the terms. And the bottom can be rewritten as 5n times 5n, and you can see that these two cancel out. So we can rewrite the series as -1 to the power of n over 5n. Now, we have to see if this hits all three of the conditions. So first, this does alter in signs because it has the -1 to the power of n. The limit as n approaches infinity of a sub n. And keep in mind that a sub n excludes the term that is causing it to alternate. So when we say a sub n, we're really talking about 1 over 5 to the power of n, because this is excluding the -1 to the power of n, and this is equal to 0. Now, I think finally we have to see if it decreases in magnitude, meaning we disregard the term, the part of the equation that's causing it to alternate in signs. So again, we're just looking at 1 over 5 to the power of n, and of course that does decrease in magnitude, because we can see we go from 1 over 5 to the power of 0 to 1 over 5 to the power of 1. So it is very clearly decreasing in magnitude. So we can say that it decreases in mag. So we must state by the alternating series test that this series n equals 0 to infinity of -1 to the power of n over 5 to the power of n converges by alt term. However, now we have to see if it converges conditionally or absolutely. So we have to say that the absolute value of this series is equal to, now I did not go over this part earlier, but to take the absolute value of an alternating series, you just get rid of the part of the equation that's causing it to alternate. So we have to state that the absolute value of this series is equal to the series of n equals 0 to infinity 1 over 5n. And we can see that by the geoterms test that this is equal to, I should probably state this. The absolute value of r is equal to 1/5, which is less than 1. So we can see that this alternates by, this converges by the geoterms test. So we have to state that. This is a bit of a long proof, however, you kind of need it. So we said that this series converges by geoterms. Actually, sorry, I'm mistaken. No, I'm not actually. Okay, and from here we can say that the original series, that being the series of n equals 0 to infinity of -1 to the power of n over 5n, converges absolutely. Okay, this is the final practice problem. It's a little bit easier than the one prior. We can take a look at the series and see that it's pretty difficult to simplify. So let's just write it as it is and see if we can, and see if it matches any of the conditions needed for it to converge. So, as I stated earlier, cosine of n times pi alternates. If we disregard this 1 over n for a moment, we can see that it goes from 1 to -1 to +1 and so on. So it very clearly alternates in sign. So we have to say that alternate sign. We also have to say that the limit as n approaches infinity of a sub n equals 0. A sub n in this instance is 1 over n, because we are disregarding the portion of the equation that's causing it to alternate, and that is very clearly equal to 0. Lastly, we have to say it decreases in magnitude, which it very clearly does, because you can see we go from, oh, I just realized this series is incorrect. This should be a 1, because otherwise the first term would be indeterminate, or undefined, I mean. Okay, so we can see that this series, I don't really want to write it out again. Let's just draw this arrow. Converges by all terms. Okay, so now we have to see if it converges absolutely or conditionally. We can do that by finding the absolute value. And you must always equate the absolute value to the simplified equation. So the absolute value of n times pi over n is equal to the absolute value, is equal to the series of n equals 1 to infinity of 1 over n. And that's because whenever you're trying to find the absolute value of a series, you just disregard the portion of it that is negative or that causes it to alternate in signs. Okay, so we can use the p series on this equation. We can see that the p is equal to 1, meaning this is a harmonic series and that it diverges. So we can say that this series diverges by p series. And since the original series converged and the absolute value of the series diverged, we can say that this series, the original series, converges conditionally, not absolutely. Okay, so that is it for this video. If you liked it, make sure to like the video and comment what you suggest I should do for the future videos.